Okay, so good morning, everyone. This will be this first lecture. I'm going to give an overview of the course and talk a bit about the goals of this course. So this why use programming for processing data. It will be in part as a motivation, but since you're here, you're probably already motivated for this, so it will be mostly to explain what our goals are in this course. And despite being commonly known as the Python course, this is not really a programming course or a Python course. This is specifically focused for processing data, and we use programming and Python as a tool, but the idea is that we get something practical that we can apply and not spend too much time in programming basics and software development or things like that. So this is specifically towards getting you as fast as possible to be able to process your data and automate the processing. And this morning I'm going to start with an introduction to Python, so the basics, and this will be a bit like learning to swim by falling into the lake. So it will be a bit tough in the beginning, especially if you don't have prior programming experience, but if you don't drown, then things will get easier eventually. So we're going to look at all the pieces that we have that we can play with, the basic elements of Python. This will be a lot of information, but then we will repeatedly use them over these 3 weeks. So things will start to make sense, a bit like learning chess. You start by, you know how all the pieces move, and it doesn't make sense, but when you start playing, then things fit together. So this will be this first session in the morning. The idea will be to start by understanding the basics of Python programming, and we will start writing something in the tutorial part, and you get to start putting some scripts to work and decompose some problems and create functions and so on. And eventually, during this course, you will start to understand how to use Python to write programs to solve your data processing needs. We're going to, after this morning, after today, in the next week, we're going to look mostly at libraries that you can use for plotting, for processing data tables and things like that. So we're going to start in the morning with the basics of Python, but then we're going to look at different libraries that make a lot of these tasks easier. And it will be basically to get you started, because if you then need to solve some more complex problems, probably you'll need to study a bit more, but if you know the basics and you have an idea of how to work with this and how to study, to learn this, then it should be easier to carry on. We're going to have this basic structure for each session. We'll have a lunch break of 1 hour between 1 o'clock and 2 o'clock. This is a bit tight, but if we leave exactly at 1, we should be able to start at 2 with no delays. For each session, I'm going to talk first, give some presentation, the lecture, and then we'll have the tutorial part. This is an estimate about 1 hour, 1 hour and a half for the lectures, but it's going to be more than that in the first ones and less than that in the last one. So we will go from more theory to more practice along the course. So one in the morning and in the afternoon. Each of the tutorial sessions has one exercise for evaluation. So if you need to be graded in this course, you will have to send in these exercises, except for the last session, the afternoon on the third day. That one has no exercise and is reserved for starting with the final assignment. For those of you who don't need to be graded, which usually is most of the participants, you can decide whether to do the exercises or to start on your own problems, whatever motivated you to be here, depending on whether you find the exercise useful for something that you need. So if you don't need to be graded, you can just look at the different exercises and do whatever you think is more useful for your specific problem, and I'll try to help you with whatever you want to work on. So this will be the main goal here. You have these 3 Saturdays with my help here. Afterwards, you can contact me by email or something like that. But this should be to get you started on solving your problems, and then you can carry on. So today we're going to start basic introduction to Python and Spider. Spider is the integrated development environment we're going to use. There are some alternatives like Jupyter and things like that. Once you get some practice, you can try other ones. But Spider is nice because it's simple. You have the files you save with the source code and the console, and it's easy to understand how everything is working.
I have one question.
Yes.
What's the difference between Python and MATLAB? Because it's very similar to MATLAB.
Well, the integrated development environments are very similar, independent on the language. In fact, there are some that you can use for several languages. The differences are in the language itself, the syntax and so on. But if you have experience with MATLAB, lots of the things will be similar. Loops and conditions and functions. There are some differences in the syntax, but the structure is very similar. Okay. In the afternoon, we're going to start seeing how we can import code from different modules, from different libraries or other code that we have written, and we'll use that to start plotting data. And then on the second day, we're going to look at libraries in the morning for dealing with numerical data, so homogeneous numerical data, matrices and so on, and in the afternoon with how to deal with heterogeneous tables that can include numbers and categories, text, and so forth. So we're going to look at the pandas and NumPy libraries. And on the third day, I'm going to talk a bit in the morning about some more advanced things that you may need to do, like write scripts that can take in command line arguments, so it's easier to fit them together with some other processing pipeline, how to create your own objects and things like that. And for the afternoon, on the third day, I'm going to give some specific examples of applications, and this would be more interesting if these examples are actually your examples, so if I can use this to help you get started with your own work. So if during this week you can send me some topics that you're working on, especially for those of you who don't need the grades, because this is a problem. Those of you I need to grade, I need to set something aside for the evaluation. So it's impossible to do both things, teaching and grading at the same time. But for anyone who doesn't need a grade, there is no limit to how much I can help. So if you just tell me what you're working on, I can give you help you get started, and can use that as an example in the final section to show you how to solve some problems. Okay. For those who need grading, the 30% of the grade will be the best 4 out of 5 assignments. So there are 5 tutorial sessions with assignments for grading, and 70% is the final assignment. That deadline is not, this was for the previous edition. I still don't know for sure what the deadline is, but we can talk about that with those who need grading and set something. It should be about in the beginning of January or by mid-December or something like that, because I need to have everything graded before the end of the semester to send it to the doctoral school. But we can arrange that, the exact date, depending on what is convenient for you. Okay? So those of you who need grading, let me know and we can discuss the date. So this is the instructions. You need to send to this address a zip file with a PDF called report that just has a short description of what the goals are and what the problem is. This should be no bigger than 5 pages, something like that. And then you need the source code with at least one code file called test.py that runs some tests and demonstrates how your program works. You also probably need a sample of data, but you don't need to use real data. So if you're working on data that is still confidential or something like that, you can just generate some example of fictional data and use that just to illustrate how the program works. I don't need to see the actual results, just the program working. Okay? So put this in a zip file and send to that address, and that's how you submit the assignment in the end. Sorry? Okay. So let's see the motivation and the goals for this course, and why should we worry about writing code. There are several disadvantages to manually processing your data. First, what you get as the result is just the processed data. If you write code, if you use programming, you get a recipe for processing data that the computer can use, and that is much more useful because you can reuse it or run it anytime you want. Also, when you process data, if you need to do it again, you have to do it yourself. With programming, you just run your program. This makes it also much less prone to random errors. There can be errors in the program, but they are reproducible errors usually. So you can easily find the error, and once you fix it, it's fixed. If you do everything by hand, then sometimes errors occur, sometimes they don't, and it's much harder to figure out what went wrong. One important difference also is how you document what you did. If you're doing things by hand, it's very hard to specify exactly what you did, which cells you selected, what you dragged, what you copied, and so forth. When you write your code, everything must be specified there with enough detail for even the computer to be able to do it. And if you write your code properly, it will also be easy to read for humans. So that will be one of our concerns here, that your code acts as a document specifying and something intelligible that you can see how the data was processed. So it will be not only for the computer to execute, but also for humans to understand. And that is one reason for choosing Python, because Python is also conceived to be a language that is easy to read by humans, not only by the computer. Another important thing is that you can reuse parts of your code for other tasks. So this would be another goal for this course, to teach you how to decompose your problems instead of writing one monolithic script that does everything, to think about how you can break things apart, build it in different modules that are easier to test, but also that you can reuse in different contexts, because maybe there is a similar problem that uses 80% of what you did before, and you just need to write the other 20% because you have everything ready to be used. So this would be two major concerns here. Write your code in a way that it's easy to read and to understand for a human being, and also write your code in a way that you can easily reuse parts of it in different problems. So this would be our main focus here: automate the processing, write intelligible code and reusable code. And so this is part of what we do in a programming course, but we will not be worried too much about general programming principles and practice. This would be focused for each of you on your particular area of expertise. So the idea is that you already know what the algorithms are, you already know how to process data, what are the methods that are appropriate for each case, and you already know those in detail, so all you need to do is translate that into something the computer can execute. And this is a major part in a more generic programming approach, which would be to identify the requirements for your problem, figure out the algorithms, and so on. So we're going to skip all that because we're going to assume that you're going to apply this to problems that you already know how to solve. You just need to be able to translate it into something the computer can do. And we're going to focus on the documentation and the way that you write the code so it's easy to understand, the names of the variables, the functions, the structure of the code, and so forth. And also so that you can easily take advantage of previous work when you continue and you want to apply, want to solve some similar problems that can benefit from reusing something you had before. So what do you need to write code? First of all, you need to understand the problem and figure out the algorithm. So basically the algorithm is the sequence of steps that you need to specify to obtain a solution. And before you can think about the algorithm, you need to understand what the problem is, what the goals are, and so on. This is often the hardest part in programming, and this is the one we'll assume is already solved. So for any problem that you're going to try to solve, either in the exercises or your real problems, you should already know how to solve them, even if you did it by hand, so you can specify now to the computer how to do it. So this is what we're going to focus most on. Think about how to decompose a complex task into simpler elements so that you can easily implement each of them, easily test each of them, and then fit them together to get the overall program working. Then we'll also look at implementation. One thing is to do this conceptually. We think about how to decompose the problem, but then we need to write the actual code, modify, test, modify, see what's wrong, fix it, and keep repeating this until we fit everything together. So this will be our focus. We will focus on this decomposition, implementation, and testing. And to work on that part, the implementation, we will need basically to know how to do four things. We will need to know how to store data somewhere, because we're going to process data. We need to keep that information somewhere where we can access it. We need to do something to the data, some operations, compute statistics, transform formats, things like that. We need to control what is done and when, if things need to be repeated some set number of times, or if there are conditions depending on the values that we have. And we need to be able to organize things. So basically, this is what we're going to look at this morning, the basic elements of Python programming that allow you to store data, so variables of different types, operators and functions that you can use to modify data, to do something to the data, how you can control the execution of your program, and how you can decompose things and separate different tasks by creating functions. So this will be what we'll be looking at in the morning. It's a lot of information, but don't worry about memorizing everything at once. This is basically you're going to learn how the chess pieces move, and then once you start playing, things will start to fit together. So we will keep using these basic elements during these weeks. So any questions that remain or things that are confusing, you will eventually be able to clarify those and get some experience on how to use these basic elements. So the idea is not that you need to know everything right now. This is just a roadmap for what we will be using during the rest of the course. Usually, when I teach this for example, a semester course, I teach one of the things on each week or something like that to make it easier, but we cannot do that here, because if we take it too slow on the basics, then we reach the end of the course and you will only know the basics, and that's not useful to do anything. So this will be a bit tough in the beginning, but the idea is that you can get something useful out of your investment here. So by the end of the 3 weeks, you can at least do something on your own and have an idea of how to solve your problem. Okay? So that will be an important goal here. To do that, we will keep using the same elements and then focus on what libraries you can use to simplify your code and to use a code that is already written to do the different tasks. But every time we will be doing that, we'll be going back to the same basic elements, so we'll be repeating the same thing during the 3 weeks. So let's start with the basic notion here of variables and types. You can think of a variable as a name for an address in memory. We don't worry about where the address is, the interpreter will take care of that, but we have a name that we can use to access that region in memory. So, for example, this var name will be pointing to this address here, and there is something stored there. The computer stores zeros and ones, or conceptually zeros and ones. It's some difference in charge or magnetic field on the hard drive or something like that, but it's a series of zeros and ones. And that will be what is stored in that address, and the interpreter will keep in memory a table of which address corresponds to which name. Now, the interpreter will also need to know how to work with these series of zeros and ones, because they can be representing many different things. So, this is determined by the type of value that we are storing in that variable, or the type of the variable. There are lots of types you can use in Python. These are some of the basic ones. None is a keyword that we can use if we want to create a variable just as a placeholder without any data yet. We can assign none to that variable. You can use numeric values, integers or floating number values, so with fractions. You can use strings. These are ordered sets of characters that represent text. And then lists and tuples are ordered sets of any kinds of values, any kind of these types that you can use, or other types, or any object you can put there. There is a difference in that tuples cannot be changed. Once you create a tuple, you cannot remove or change or insert elements. This is useful if you use for things like coordinates, in which the position in the set determines the meaning of the value. So you have the x, y, and z, for example. It makes no sense to remove one, because then you don't know what the others mean. Lists are usually used for homogeneous values, say a list of years or something like that, where it can make sense to remove some or replace some elements. And then we have dictionaries which pair keys to values. So it works something like a phone list, where you have the names and the phone numbers, or a dictionary where you have the words and the definitions. So anytime you need to make a correspondence between pairs of values, something you use to access the value that is associated with it, then you can use a dictionary. And to tell the interpreter what kind of value it's going to store in those zeros and ones, we need to have some syntactic indicators to specify the value. So you have this keyword none if you want to just create a placeholder variable without the values there. If you use a number without a decimal point, then the interpreter assumes that to be an integer, and it stores it in a specific format. A number with a decimal point is a floating point number. It has a different format. A string is a sequence of any set of characters enclosed either by single quotes or double quotes. If you do it like this with single quotes or double quotes, then it cannot have a line break, so it must be all in one line. If you want to have a block of text that spans several lines, you can start with 3 of these characters, so 3 single quote characters, and then end with 3 of them. And in that case, you can store a block of text with several lines. For lists, you use the square brackets, and the elements are separated by commas. The elements can be anything. They can be numbers or any other kind of object. The same thing for tuples, but you use the parentheses for tuples. Dictionary starts and ends with curly brackets, and then have the key and value pairs separated by colons. So you indicate that fox is a key, and the value is a mammal, and so forth. The keys for dictionaries need to be something that doesn't change, like a string or a tuple or a number. It cannot be a list, for example, because the dictionary must keep is stored in a way that optimizes the search for each key, and if the key changes, then things won't work. So the dictionary doesn't let you use keys that are mutable. The values that are associated can be anything, because only the keys have that restriction. So you don't need to memorize this all at once, but this is something that will start to become part of what you remember as you use it. So if you use it several times, then you eventually remember the different syntaxes. The important point here is to remember that the interpreter will look at what you're writing to decide what kind of value you are trying to store in the variable, and this is always the same pattern. You specify the name of the variable, you have an equal sign, this is an attribution operator, so you are telling the interpreter to store that value in that drawer, in that name, and this will create on the interpreter's table this name. It will be pointing to an address in memory where the value is stored, and the interpreter knows how to interpret that value, what is the meaning for that value. Then you can do also things with data. You have these basic operators like sum, division, and so on. There are two division operators. This one slash will do the usual division, so 5 divided by 3 is 1.666 and so on. If you use two slashes, this is integer division, so you have the division but the remainder is thrown away. So 5 divided by 3 will be 1. This is if you want to retain integer values, if you are dividing integers and want the answer to be an integer too. You can use most of these operators also with strings and lists, so you can concatenate these sets by using sum. You can multiply them by an integer and have a set of copies and so on. If you want to do exponentiation, so 4 raised to the power of 2, this is 2 multiplication signs. So in other languages, for instance in MATLAB it's a hat sign, but here it's 2 multiplication. There are also comparison operators. You're asking if 5 equals to 2 or if 4 is less than 8. Remember then that the equals when you're doing a comparison is not the same as the equal here when you're doing an assignment. So an assignment is one equal sign. If you want to do a comparison, you need to put 2 equal signs. If you were to write 5 equals 2 with 1 equal sign, you would get an error because you cannot assign anything to 5. 5 is not a name for assigning values. You can also ask if something belongs to a set. So you have this in operator that you can use to determine if a value is present inside a set. So this is a simple example for computing a concentration. We want to compute the concentration of 2 grams of salt in 100 milliliters of water, and we can use variables to make it easy to understand the code. So this would be the molar mass for salt. This is the mass that we have in grams in our solution, the volume of the solution, and then we can compute the concentration by dividing the mass by the molar mass and the volume and print out the result. So this, I'm going to use this representation here on the slide. Whenever the background is yellow, I'm referring to something that we're going to write in a code file and save it to the disk. So this would be our nacl.py file. This py extension is the convention for Python source code file. So this, you can do this in Filer, create a file, save the file, and then you can run the file by pressing F5, and it will run on the console, and I will be representing the console with this gray background. So this is what you can see in the console when your program runs. Everything that your program does is not echoed to the console. So for those of you who are used to MATLAB, for example, Python works differently here because it doesn't show you all the intermediate steps. It only displays on the console what you tell it to display. And you tell the interpreter to write something to the console with the print function here. So you have print, you open parentheses, and you specify what you want to print. If you want to print several things, you can separate them by a comma. So I'm going to print the string concentration, and then the value of in the conc variable, the concentration variable, and then an M. And this would be what appears on the console. When you have arrays such as strings or lists or tuples, so anything that has a set of elements in order, you can specify which element you want by indicating the index for that element. Just remember that in Python, the index of the first element is 0. So indexing starts at 0. If you want the first element, it's index 0, second element index 1, and so on. You can also index from the end. If you specify a -1 in the index, then you're asking for the last element, and you can go backwards from there. So these are some examples. Here we can have these are examples of here. From this string, the character with index 2 is the D character there. So it's the third one because the first one has index 0, 1, 2. This is true for lists, tuples, and strings because they have an ordered set of elements. Dictionaries are different. The idea of having a dictionary is that you don't care about the position in the dictionary. You want the values corresponding to some keyword, to some index there. So if you have this dictionary here, you can access each value stored in the dictionary by giving the corresponding key as an index. So if I ask for animal classes of fly, it will go and get the insect key and output the insect. If you do this in the console, anything that produces a result, if that result is not stored in some variable, the console will echo it. So if you do something like this, name equals to a string, the console will not tell you anything. It will simply store the name, the string in that variable. But if you do something like this, name2, this will output some value. And since you're not putting that value anywhere, the console will echo the value. This is practical if you want to look at the value in a variable, or look at an entry in the dictionary, something like that. When you have these ordered arrays, lists or strings or tuples, you can also slice them by indicating a beginning, an end, and how many elements you want to skip in between. So basically, you say the first slicing point, the last slicing point, and the step. These are all separated by columns, and you can imagine if you're going forward in the array, you can imagine that the slicing points fall between the elements. So if you ask between slicing point 1 and 3, you get these two elements here. You're cutting the array at those points. You can omit any of these. And if you omit the step, the interpreter will assume that the step is 1. You want every element in that slice. If you omit the end, it will assume that you want to go to the end of the step. If you omit the beginning, it will assume you want to start at the beginning. So, for example, if you write name 03 here, we are omitting the step, so the interpreter will assume that the step is 1, and it will go from slice points at index 0 to the one at index 3, and it will be this from here to here. So you'll get the first 3 characters of the string. Okay. If we do it like this, this means we are omitting the beginning, the end, and we are only specifying the step. So it goes from the beginning to the end of the string, and it jumps 2 characters. So it gives us every other character from the string. We can do the same thing, but starting with slice point 1. In this case, I gave the beginning, but not the end, so it will go to the end of the string. So basically, this gives us the odd characters, and these the even characters from the string. You can also index from the end of the string using negative index values, or even if you use a negative step, you can reorder the string, so invert the ordering of the string. Now let's see an example here where we're going to solve a quadratic equation, and we're going to create a list eventually with the solution for the the equation. So we're going to, this would be the first version. We are assuming that this part here inside the square root is positive. So just to, for those of you who might not remember, this is for solving a second degree equation. You often have two solutions, which are the values of x for which y is 0. So if this part here inside the square root is positive, this would be for a polynomial that has x squared times a, x times b, and then plus c at the end. If this part is positive, we have two solutions, and we can compute that part here. So b squared minus 4ac, this is the part inside there, and we can compute the square root of that by raising to 0.5, and we compute the two solutions for this polynomial. So here we have the coefficients a, b, and c, and here we have a list starting with square brackets, ends with square brackets. There is a comma there. This is one of the solutions, and the other, so the two roots for the polynomial. And then we can test the results. So if we replace x with each of these roots, we should get a value that is very close to 0, because that is the solution for that equation. So this would be, if we run this, we can then ask for the value in the solution variable, and this list with the two roots, and we can ask for these two values, epsilon1, epsilon2, and we have the two values here, which are 0, so we have tested our answer. Note that you can do this, you can create a tuple by indicating with a comma different variables or different values. So the console here is outputting a tuple with the values of the two variables there. Now, we are assuming that this is positive, because if it's not, then this would be wrong. We wouldn't have, we could have only one root, or we would not have a real answer, a real solution for the equation. So we can we can run our code in different ways, depending on the value of that delta term there. And to do that, we can use this if statement. This is one example of how we can control the flow of the execution of our code. We write the if statement and then one condition, something that can be evaluated as true or false typically, and then a colon there, and afterwards indented we specify the block of code that will be executed if the condition is true. This is the basic if statement here. Just if condition and something that will be executed if the condition is true. If the condition is not true, then that block will not be executed. If we have alternatives that we want to check, we can use these elif branches here. So this elif is a contraction for else if, and it means that if the first one failed, or if all before failed, the condition, then this condition will be tested, and if it's true, then this is the code that will be executed. In any case, these if structures will only execute one of the blocks of code. As soon as one condition is true, then that code is executed, and the interpreter exits the if. So if you have several conditions, only the first one that is true will be, that block will be executed. The others will be ignored. You can also have you can have any number of elif with conditions here, and you can have one else branch, and this means that if all else fails, you can execute this part. But all of these brackets here are not part of the syntax. They are just to indicate that these are optional elements of the if structure. The only one that you need is the first one, if some condition. So let's see an example here. We can compute delta, and then we check. If this delta value is below 0, this means that this part is negative, so we don't have any real solution for the equation, and we assign to the solution variable this empty list. This means there are no solutions. If this one fails, then the interpreter will check this other condition, the LE. And if delta is greater than 0, then we create a list with the two different roots for the polynomial here. Otherwise, if both of these fail, then this means that delta is exactly 0, and in that case we only have one answer, and it's that one. So the list will now only have one element. So this is an example. We could do this with only one branch if we had some different conditions, or only with if and else. You can use that depending on what the situation is. And then in the end we can write this print solution values are and the solution in our in the console. So the way we can use this script is we assign some values to A, B, and C. Note that the script assumes that A, B, and C already have values there, because if they don't have, the script will not work. When it will try to compute this expression, it will give an error because there are no values in the variable. So we need to first assign some values to the variables. This would be for a polynomial 2x squared minus 3x plus 1. This will be the A, B, and C for this one. And then we run the script. We can press F5 in Spider, and it will run all these codes and give us the solution value. If we try with a different polynomial, for example, this one has no real root, so it will give us an empty list. This one has only one solution there. Note that we get a -0 here, but this is a problem that you'll have often with rounding errors. When we compute the square root of something, often we can get some number that has an infinite number of decimal places, but since the numerical representation is finite, there will be some truncation there, some rounding error, and so you can have something that is very close to 0 but not exactly 0. Another structure for controlling the flow of executing our program is this for statement that allows you to repeat a block of code for different instances, so a given number of times or once for each element in some set. So the way you specify this is also similar syntactically to how you do the if branch. You have the statement, in this case it's for, and then you have this column here, the 2 points, and then everything is indented that belongs to the for. So if you are used to other programming languages, this is something that is a bit unique in Python, which is indentation is part of the syntax for the language. So other languages often have a begin, end, or something like that to indicate where each block ends. In Python, the blocks are determined by the indentation here. So the interpreter knows that this line belongs to this block on the if because it's a bit ahead of the if there. When it goes back to the same alignment, then it's another branch for it. The same thing for the for loop. So you have for year in this list, column, and then you have this instruction here, print, which belongs to the loop. It's inside the loop and will be executed for each step of the loop. The for loop, how it works is you specify a name for a variable that will be used to point to each element in the set that you're giving to the for instruction. So in this case, the variable year will start by pointing to the first value, 1991, and this line will be executed with year pointing to that value. And then year will be pointing to the second value, and the line will be executed again, and so on. So you're going to execute this block of code for each element in this set, and the variable there will point to each element in turn. So this is what you get in the console if you run this code. You get the same thing repeated 3 times, and for each time the variable year is pointing to a different element in the set. So we can improve our code, our script for solving quadratic equations by creating a list of tuples with different polynomials. So each of these tuples has an A, B, and C, and there are 3 polynomials specified here. We create a list with all of these polynomials, and then we loop through all these lists. So this variable for the coefficients will point first to the first tuple. Note that the elements of the list are not the individual numbers, they are the tuples of 3 numbers. And so in this loop, this coef variable will point to the first tuple, then to the second one, and then to the third. Since there are 3 tuples in the list, all this block here will be executed 3 times. Now, what we're going to do inside the loop is to unpack the tuples into the 3 different variables. And this is something that is useful that you can do in Python if you have an ordered set of values, like a list or a tuple or even a string, and you have the same number of variables there as the elements in the set. You can just assign each element of the set in order to those variables using this syntax. So since we know that all these tuples have 3 values, and they are always A, B, and C, we can just unpack each tuple into the A, B, and C variables in this way. And now we have A pointing to that 3, B to that 2, and C to that 1 in the first iteration of the for. Now we do what we did before, but note that everything has this indentation, because everything here belongs to inside the for loop. This means that it's going to be executed once for each element in that list. And now we check the delta, we compute the solution, and we print the solution. So we print the solution for this coefficient is, and we print the list of values there. So when we run this script, we'll get 3 printouts there, one for each of the elements here on the list, for each of these tuple of 3 values, with the corresponding solution for that equation. And this is how the interpreter knows that all of this code is inside the for, because it's indented, but then this line belongs inside that if, this line belongs inside that branch, and so on. So the indentation here is important for the interpreter to know where each part belongs.
The print should be relaxed.
No, because we want one print for each iteration in the loop. If you align the print here, you would only print the last solution, okay? So this is something that sometimes happens. If the print was here, it will only print this case here, because it's the one with only one solution, because it will belong to this branch. If it was aligned here, it will only be executed after the loop finished, and will only print out the last solution, because that was what was left on the variable, okay? So you need to understand exactly where to place each line of code for things to work. Okay, so this is one example where we just dump everything into a script and we do all of it in sequence. One problem here is that we need to specify everything in advance, which are our equations. This is part of the source code, and this is not very elegant because it's very rigid in the way we can use it. So we're going to improve that by looking at functions. When you solve your problems by creating just one script, one major problem there is that you cannot reuse parts of the script. So here, in this example, we have everything together. These are the equations we're going to solve. This is the loop, this is the check for each one, and so forth. And everything is glued together. We cannot separate this easily. There's also no good way of controlling what goes in and comes out of our script, because what goes into the data that we're using here are basically those values for the polynomials, but these are already written into the script. We have no control over that from outside the script. And the output is always the printout of the solution. So if we wanted to take the actual values and use them somewhere else, this would not be very practical, because we just have them printed out on the console, and now we don't have them available for using. And another problem is that everything is mixed up, all the variables. So look at what we did here before. We created these variables in the console, then we ran the script created new variables, and we could look at the variables there in the script. But notice that this is dangerous, because if we combine several scripts, if the variable names collide, then one can be interfering with the other, and eventually things become increasingly complex as we try to bring more pieces together. So the basic idea of functions is to solve these problems. We can control what goes into the function, what comes out of the function. The code inside is autonomous, and it's isolated from the outside. So the variables that are created inside the function only exist inside the function. This is very important because once we know the function is working, we know it cannot stop working just because we use some variable outside with some name that collides with something inside the function. Because it's isolated, it operates as if it had a universe of its own without outside interference. So how can we do this? We use this def keyword, define a function, and this is followed by the name of the function we want to create, and then inside parentheses we need to specify the names of those variables that belong to the function, which will receive the values we want to provide the function with. So if we have a function to solve a quadratic equation, the function will need to know the coefficients of that second degree polynomial, so the a, b, and c. We can then follow this with documentation with a string that can describe how the function works, and this can be useful for someone who will then use the function. And we write our function exactly in this case in the same way that we did discrete. We compute this discriminant, we check if it's below 0, greater than 0, or equal to 0, and we compute the solution. But then we have full control over what comes out of the function. And this is done here in this statement, return, which can be just to exit the function. When the interpreter encounters return, it will exit the function. But if return is followed by some value, when the interpreter exits the function, it will return those values, a copy of those values to whoever calls the function. So in this case, the values that are stored in solution will be returned to who calls the function. And we can now run this script. When we run this script, the interpreter will not compute anything. There is nothing there yet to compute, but it will create an object called solve quadratic, which is the function. And this can be executed by calling its name followed by the parentheses. In this case, since the function also needs to know the values it will compute, inside the parentheses it will need to have those three values, the a, b, and c. So this is what we do. We run this code, the interpreter will create this function in memory, and now we can execute the function by calling the name of the function and specifying in parentheses the three values for a, b, and c. And then the function will compute the result and return the result. Since we are not placing the result anywhere, we see the echo here in the console. But we could easily just assign it to a variable and store the result to use in some other computation. So this is one way of creating the function and using a function. One big advantage here is that now we can use this function for whatever polynomial curve of second degree that we want. We just change the values of the coefficients and it will compute for those values. Another advantage is that we don't necessarily have just a printout of the result, we have the actual result. If we want to print it, we can print it, but if we want to compute something with it, we can also use it. Here in this string, you can also write documentation for how to use your function, and this will be used by the help function. When you write help and the name of the function, this help function will look for the documentation and print it out. So you can write here some instructions that make it unnecessary for the user to actually go read your code. They can just write help your function and they see how to use it, what the function does. And this is also something that you have in functions that are already implemented in Python or in the library. So this is a standard way of documenting code. So if you want to know more about a specific function, you can just write help and the name of the function. Now here there is, notice this difference. Here I'm writing the name of the function followed by the parentheses. These parentheses after the name tell the interpreter that the interpreter is to execute the function. So the function will actually be, this code will be executed. If you just write the name of the function, you are just referring to the function. So it's not going to execute it, you're just talking about the function. So this is what you do when you call help on the function. This is just to tell help which function you want help about. Another important advantage of creating functions is that the variables inside are isolated from the outside. For example, suppose that we call this solve quadratic with these values. In this case, the delta here is 0. The function computes everything, returns the solution, but if we ask for delta, we get this error. There is no variable named delta. That's because the variable delta inside the function only exists inside the function. It does not correspond to any delta outside the function, even if there is a variable with the same name, and it does not exist once the function ends. So you can actually have some delta value here, some variable named delta. You call the function uses the variable named delta, but it does not change your variable delta outside. This is an important feature of functions because it allows you not to worry about the names of the variables inside the function. It's not relevant because they will not affect anything outside. And this is what enables us to build complex programs out of simple steps, simple functions. Because once the function is working, you don't need to worry about interfering with anything else. You can just fit things together and build a more complex program. So this would be our script for solving quadratic equations. We could write it like this. We have the function here to solve a quadratic equation, and we can have a set of steps here. When you run this in Spider, for example, it will create this function and then execute the test. Note that the tests do not belong to the function. They are indented here, and the body of the function is this one here. So when you run this, it will automatically run the test for your function in this way. So to recap important features of functions, they are isolated, so you can reuse, you don't need to worry about the names of the variables inside the function. You can provide an abstract recipe. This is a recipe for solving the quadratic equation regardless of what the actual coefficients are. So the coefficients are there as variables, they can be anything. And then you can solve concrete examples by providing the values that you need to work on. And this is what allows us to decompose the complex problem into simple steps that then we start fitting together until we have everything built. So in general, you will not write complex functions. If you have some complex tasks to do, you split it into simpler tasks, write and test each of the parts, and then start assembling everything. To create functions, you use this def statement. This is an executable part of your code that will create the object with that name that is specified. So in this case, it creates a solve quadratic object that has the function that you can use to execute. And then once this is executed, you have this name, this variable, so to speak, with that function of the test. So remember this, because if you, especially if you come from MATLAB, where all you needed was to save the source code file and then the function will be changed. In this case, if you change the function, you need to run your code again, so that the function gets redeclared in memory, so recreated in memory and is updated. To use functions, you use the name of the function and followed by parentheses. Even if your function has no argument, so even if it doesn't need to receive any value, you need to put parentheses there to tell the interpreter that he is to execute the function. You pass the arguments by position, so by order. In this case, it's A, B, and C, so this is A, B, and C. You can also give them by name. You can put here, say, C equals 1, and the interpreter will understand that this one would go to C there. And then the return statement, when the interpreter finds it in the function, it exits the function. Usually the return statement is at the end of the function. If there is no return statement at the end of the function, the interpreter exits the function and returns a none variable, so the function does not return anything. If the return statement also does not have a value there, it will return a none value at the end. You can put the return statement anywhere in the function, but remember that as soon as it's executed, the execution exits the function. So everything after a return statement will not be executed. But there may be some conditions, so if you want to exit the function early, if something happens, then you can do that. Okay, so let's stop a bit here the theory and look at this in practice, also to rest a bit. So I'm going to, this is the exercise, a simple exercise is we have this dictionary with the keys are capitals and the values are the countries they are capitals of. And we can create a function that tells us the capital of the country with the longest name. So this would be one exercise to show how to fit these things together. And basically what we're going to do is to start with a small value, for example 0 or -1 or something like that, for the length of the name of the longest country, and then loop through all the dictionary and update this value every time we find a larger one. So if we do that, we can get the largest value at the end. So this would be the algorithm that we're going to implement. But I'm going to also go through a bit of the other elements here. This is, I just copied this here to speed things up a bit. But if you probably already played a bit with Python with that first tutorial. But just to recap, this is the interactive console here. It's interactive because if you do something here, then you get the output at once. Okay? So everything you write here is immediately executed. For example, I can create a variable with a list of values. Note that it does not need to be a homogeneous set of values. It can have anything there that you want. So this is a list. And now, for example, I can loop through this list for val in A, and I can print val. Note that when you write a block like this in the console, since you ended with this column here, this is something that requires a block of code that belongs to it. So the console is not executing my code yet. It's waiting for me to write everything before it can execute. So I now write this line, this print line here, and if I press enter, it won't do anything yet, because I could want to write more lines inside this block of code. It will only execute in this case when I press enter again, and there's an empty line, then it knows I finished writing the block of code, and it will execute. So what are we doing here? A is this list of values. Val will point to each of them in order, and for each of these iterations, the interpreter will execute this command. So it will print 1, 3, D, then 4, and then this tuple here. Note that this is a tuple with two values, but it's one element of the list. So it will not loop through each of the values in the tuple, it will just pick out the tuple and write it down. So this is an example of creating a variable, creating a list, and looping through the list. This part here is where you write your source code. So let's start a new one. This line will appear if you are using Linux. If you are using Windows, it will not be there, but don't worry about that. This is just a directive for if you want your code to be executed in the shell. This is important, so don't remove it, because this tells the interpreter that this file will be saved in UTF-8 format. This is a text formats, and it allows you to use special characters like accents and things like that. Then there is a documentation here that you can edit. So this is a test code of something, but this would be the documentation for the module. And now we can save this somewhere. Save as. So you can save this into whatever folder you want with whatever name you want. So you can organize things by fashion or something like that. If you are writing something for your work, usually it's practical to save the code. If you are just doing some quick script, save the code in the same folder where you have your data files. This makes it easier to access than the files. If you want to separate things, then you just need to specify the path. So this, in this case, if I do something like this, say L equals 1, 2, 3, print L, and save, then nothing happens, even if you save your code, because you are just saving a file with the code written there. If you want the interpreter to execute your code, you can press F5 or that play sign there, and then it will execute all the lines of code here. Also note then when you press here or F5, you have this executed here. So it will run this file untitled.py in this working directory. The first time you do this, it will probably pop up a window to ask how you want to configure this, but just leave the default. This means that when you run a file, the interpreter will be running it in that folder where the file is at. So if you want to access other files and so on, you know you're starting from that location. So let's create our code here. I'm going to copy here our data. Let's leave this inside our code to make it easier to test things. And now we have, if we run this code, I'm going to press play here. We don't see anything happening in this case because I'm not telling it to display anything. But since we ran the code, now we have this dictionary here defined. So we have the capitals created this variable. And we can see, for example, what happens when we loop through a dictionary. Note that this is something that you can do easily. If you are not sure if you can do something in Python, you can just try it out, because the worst thing that can happen is that it will tell you it cannot be done, so that's not a problem. If you want to figure out, for example, what happens if we use a for loop with a dictionary, then you can see here. It will loop through the keys of the dictionary. The order may not be the same that we specified. In this case, by coincidence it is, but it may be some different ordering, but it will go through all the keys in the dictionary. So if we want the values, we can do this and get also the value for each key. So in this case, I'm going to print the key here, and then followed by the entry in the dictionary that corresponds to that key. So I have Paris, France, Lisbon, Portugal, and so on. So now we know how we can loop through a dictionary and get the values from inside the dictionary. And now we can start to implement our function. We want a function that tells us what is the capital of the country with the longest name. But we can write this function more generically. For example, what is the key for a dictionary of strings that has the longest value there? So when you think about how to name your variables or your functions, you can think about how you're going to use them and what would be the proper name for the object that you're creating. Okay. So let's say we want to call our function longest value. We create a function called longest value. Since we cannot separate parts of the name with spaces, because space indicates to the interpreter that that's a new thing that's appearing there, we can use underscore to separate when we have composite names. For example, longest value, we write longest underscore value. And this will receive a dictionary of a set of values. So we can say, for example, we call it a dictionary, and we can write documentation here. Return the key for with the longest value. And now I'll just write this down this way. So a pass is something that you can, is a special statement that you can use whenever you have a block of code that has nothing in it. This may happen because you don't want to do anything in that particular condition, or because you still did not write that part, but you want to test what is written so far. So in this case, if I don't have a pass there, it will give me an error because the function needs to have something in its body. So I want to test if this is working okay. I just put that pass there. I run the script, and now I should have a function called longest value. If I write just the name of the function, I get this output here. It's telling me that this is a function. This name refers to a function. If I write this function with something in there, it doesn't matter what, because the function is not doing anything, then it will execute the function and return nothing, because the function is not doing anything. So nothing will appear there. But I can also already use help on my function here. So you see, if I call help on my function, it will tell me that this is a function in the main model, and it will output the documentation that I specified for the function. So here, returns the key with the longest value for that dictionary and so on. So you can actually write, I'm using these three quotation marks in the beginning and the end, because I can, this way I can write my documentation in different lines. So input is a dictionary with strings as values, for example. So this would be a requirement for the function to work. If I run my script again and now ask for help, it's now updated the documentation for the function. Okay, so this is a basic thing so that it's easy to for you and for others that are going to use your code to understand what the function does. But now we need to implement the algorithm here. So we can think about finding the longest value. All strings will have at least 0 of length, because if they have nothing, they have a length of 0. We can get the length of the string by using this len function. For example, len of this string ABC is 3, if it's like this. So it tells us how many elements there are in that array. And I can do it, say, the longest largest length. I can start it at, say, -1, and longest key I can start it with a none value. So at the beginning I don't know what is the key for the longest country or for the longest value here, and I still have nothing, no length to compare with. So I start this longest at -1, and now I'll loop through the keys in the dictionary, because I know this is what happens when we look through a dictionary. So when we look through a dictionary, we get the keys for that dictionary, and I can get the value is on the dictionary. I can access the value from the key, and now I can check if the length of the value is largest than the largest length so far. So this means that I found a capital with a country that has a largest name than the one found so far. In the first iteration, this will always be true, because any string will have a length greater than -1. So it will store the first one there. But then it will only change this, or it will only execute inside this code if it finds a largest one still. So if it finds a larger one, we update the largest length, and we update the key, the longest key. Now, at the end of this, we return the longest key. So, what will it be doing here? First, it will start, let's say, with Paris. So this key would be Paris, the value would be France. The length of the string France is larger than -1 because it has several characters. So it will update this. It will store Paris here as the key, and it will update the largest length so far. Then it will find Portugal. Portugal is larger than France, and it will do this again, and so on until it has the largest one. Because if it finds something that is not larger than the one it had before, it will not execute this part of the code, so it will not change those variables. So this is an example of how we can implement the algorithm. We can now run everything. So this is now created in memory, and we can run our function longest value, so the key with the longest value for capital. And now we get here London because it's United Kingdom. So if we add something else, say Madrid or Spain, this is not longer than United Kingdom. So if we run, if everything is working, we should get the same result here. So let's say we change this to UK. Now I run everything again so that I redeclare this dictionary here. And now we get a new one because now it's Portugal that has the longest name. So this is a simple, not very useful example, but a simple example of how we create the variables, how we implement some code. Note that we have several levels here. We have this first indentation for everything that is inside the function. Then we have this for everything inside the loop. And here, what is inside that condition whenever we find the longest one. We can have this inside our script to help us test. But usually when you write code with several functions, then you may leave this out either in some testing file specifically for testing or some other way. So this might not be useful to be left there at the end. But this would be just to demonstrate how we create these functions. Do you have any questions about this part? Okay, so this also, it's important for you to understand that this part is what you're saving to a file. We have this in the file. This is what you're doing interactively to test things out, to see the outputs, and so on. So now let's see. I've sometimes talked about objects here, and this is Python is an object-oriented programming language that uses objects, so all its values are actually objects. And the idea of an object is that it not only stores data, it also includes methods, functions that operate on the data. So you can think of all these variables and all these values that you use in Python as mini programs that can also do things and not only store data statically. For example, if you create a variable with a string, or if you have some string, the string is an object that not only has that sequence of characters, but also has some methods that can operate on those values. For example, this split method here allows you to return a list of fragments of the string by cutting the string wherever it finds the substring you specify. So you tell the interpreter that you are using the split method of this string with this notation. you use the name of the variable or the string itself, a point there, and then the name of the method. In this case, the split method needs one argument, which is the substring that it will find inside your string and use to cut your string into fragments. Wherever it finds this substring, it will delete that part and return a list with everything that is left over. So in this case, we're going to split on the comma, and we get a list of all these ingredients for the soup. Then we have other methods, for example, this to return a copy of the string converted to uppercase. This one tells you if it starts with some substring or not, and so forth. There are many methods in the string, so it's not useful to memorize all of them, but if you want to do something with strings, it's useful to Google to see if there is a practical way already implemented for doing what you need. So this is the basic idea in Python. Everything that you create is an object that not only has what you ask the interpreter to store there, but also some functions, some methods that you can use to operate on your data. Okay, so I'm going to give a slightly more complex example just to finish this part, to show you how to bring together these different elements and to give you an idea of what eventually at the end of this course you should be able to do to solve your problem. So let's take a list, an input file, a text file that specifies the name of structured files from the protein data bank. Now probably those of you who come from biochemistry or things like that, which tends to be most of the participants in many of the editions, probably heard about proteins and protein structure. Those of you who come from other areas, this will be a bit strange, but basically these protein data bank files are just lists of the atoms and the coordinates of the protein, so specifying the shape of the molecule and also specifying what are the amino acid residues that compose the protein. So we can get information from the composition of each protein and the structure from these files. And let's say we have a number of these files in our folder. We also have a text file specifying which of them we want to process. So this would be the input file, a list of the file names we want to process. And this is the output that we want. We want a table that has for each of these PDB files the map of the protein in Dalton and the length of the protein in angstrom. The length would be the largest dimension of this molecule. So we want to output this summary here. The PDB file format has lots of data there, but the part that interests us is where it specifies the composition and the structure of the protein. So it has all these lines, one for each atom. It has here the X, Y, and Z coordinates of the atom in angstrom. Here the amino acid residue, the amino acid type for the residue the atom belongs to, and what the atom is. So what we need to get the map is basically we need to read the list of all the files we're going to process. For each PDB file, we need to get the list of amino acid residues it has. So a protein is built in the organism by attaching a sequence of amino acids. And so we need to find out which are there to be able to compute the total mass for the protein. And we also need the coordinates because we need to measure the largest distance between any two atoms. And then once we have these measures, we need to write to the report file. So this is an example that is specifically from biochemistry, but the idea here is to give you an example of something that is very common for you to do. You have several data files, you need to bring everything together and output a report. So this is a general problem in whatever field you're working that you probably will have to solve. And this is a good candidate for automation because once you automate this, it doesn't matter how many files you need to process, you just let the computer work and you tell your supervisor that you're working and you will have a copy or something like that. So programming is very good for that approach. So first thing we need to do is to decompose the problem into small pieces that we can immediately see how to implement. So whenever you find something that seems a bit complicated to do, stop, break it down into simpler parts until it's very clear how you're going to solve each part. So, one thing that we need to do is to list all the residues in the PDB file. We can see here that there are some identification numbers for the residues, because each one can have several atoms, so it's repeated in the file, but each one has a single identification number. So we can go through the file and find out for all the lines that start with this atom keyword. We can see if the identification number has changed, and if it's changed, it's a new residue, and we just store that to the list. So we can see how we can solve this problem. This would be one of the tasks that we can do. We can also, we need also to get the masses for each residue, so we need some table that tells us that alanine has this mass, serine has this mass, and so forth. And we can read that table into a dictionary so that we can find the mass by the amino acid code. Each amino acid type has this 3-letter code, so if we put in the 3-letter code, we get the mass. We also need to add all the masses for the residues to get the mass of the total protein, but that should be easy. Once we have the list of residues and the masses, we just loop through everything and add it all up. And we need to obtain the coordinates for the atoms. This part is also easy because each line that starts with atom has the coordinates in these positions of the string. We know from the documentation for the PDB format, so we just need to read those positions of the string and use those numbers. Then we need to measure all distances between all pairs of atoms. So here we can do 2 for loops and consider all the pairs of atoms, measure all the distance, and store the largest file. And finally, we get all the values and we write everything down to the report file. Notice that we need to do a lot of work before actually starting the programming, because we need to know exactly what each function will do before we can write it. So this is a common mistake here, is that when you need to write some code, you start by opening Spider, writing the code, and so on. And that's usually wrong, because unless you know exactly what you're going to tell the computer to do, there is no way the computer will do what you want, because you need first to know what you're going to write. So take some time before starting to actually write the code to make some scheme, some diagram or something like that of how you break down the problem, until each of these tasks is something that you know how you're going to implement. So at the moment you probably don't know how to implement these tasks, but after a few weeks you should start to be more familiar with this and be able to identify those simple tasks that you can work on. And then you figure out where you can start. You need to start from those that do not depend on others. For example, it's not a good idea to start with the function that writes the report file, because this one will need all the others and we cannot test it until we have the others. But a function that, for example, lists the residues in the PDB file, this one will not need any of the other functions and we can write it down and test. So once we figure out what to do in what order it's easier to implement, then we can start implementing each of them individually. And now we shift gears, because at this point we are looking at the whole problem and how to decompose things. When we have done the decomposition and start the implementation, we are going to look at one piece at a time. So we don't need all the confusion about what we're going to do with each of these elements. We just need to focus on each of them. So we know we need a function to list all the residues in a PDB file. We're going to just write that function. We don't worry about the rest of the problem. So one thing that you can do, and you can take advantage of that path keyword that I omitted here for saving space, but you can just write in your source code all the functions that you're going to write and put a path there, write the documentation and so on. And this would be a good way to start having a roadmap for your program. Because not only are you thinking about how to decompose the problem, but now you're thinking in detail what each function needs to receive in order to work, and what it outputs. You can write in the documentation what the function outputs. And this allows you to check if things will fit together. Because sometimes you may find that what you need in one place you are not getting from anywhere else, so you need another function, or you need to take care of how this function outputs the results so the other one can use. And by writing things down like this, it's easier to identify those problems and solve them before you start actually writing the code. So this would be the second step, where you have a specification of everything. Of course, this is something that you will seldom end up doing, because we want something really fast, but just keep in mind that this is what you should do if you are taking things easily and don't want to have them waste more time with problems that come up later and so forth. As you get more experience, then probably you just keep this in mind. You have a clear idea of what you want. You don't need to do all these little steps. You can just write code. But in the beginning, it's useful to do this in a more systematic way. So, first function here, list residues. We have this in the PDB file. So all these, there are lots of lines that don't start with atom that have other information, but those that start with atom always have this format, and we can check the ID number here on this column to see if we have a new residue. So basically, we're going to iterate through all the lines in the file. Every time a line starts with atom, we check if there was a change in the ID number for the residue. If there was a change, then we copy this part of the string and add it to our list, so that we get a list of all the residues in the protein. Note that we cannot look at changes on this column, because it may happen that we have two residues of the same type in sequence. In that case, we need the two of them, otherwise we don't get the correct match. So we need to check the ID number to make sure. So this is the code for this function. We will get as an input a list with all the lines in the PDB file. We'll see later how we can, we see here how we can get all these lines, but the idea is that we want to minimize the time our code takes to run, and if you're always reading from the file, it can take a bit longer. So we read the PDB file into memory, into a list of strings, and then we use that for all the functions that need to process the PDB file. So this function will receive a list with all the lines in the PDB file and process that. We will start by creating this placeholder variable with a none value that is the old identifier. This is the one which will check if the identifier changed. So you need to start it with some value that is not present in the PDB file. We can use none for that. And this residue is the list of all the different residue types of the different amino acids in the protein. And now, for each line in that list of lines from the PDB file, we're going to check if it starts with atom in all caps. These are the lines that matter for us. If it does, then we're going to extract the residue name from this part here. So this code, three-letter code here, and we're going to get the ID from this part of the string. And here I'm converting it to an integer. So if you extract something from a string, even if it's all numerical characters, it's still text. It's 1, 2, something like that. If we want to convert it into a number, then we need to use a function like this, for example, int, to convert it into an integer number. In this way, the identifier is actually a number for each of the residues. And now I'm going to check if this is different from the old identifier. For the first one, it will be for the first line, because I start the old identifier with a none. A none is not equal to whatever number is there. But then, if there is a copy, there is another atom of the same residue, it will be the same, so it will not insert a new residue there, only when the value changes. So this is something similar to what we did for finding the longest one. In this case, we're looking at differences, not larger, but it's the same idea. So whenever the... Yeah. This is not equal. This is one of the... Okay, thank you for asking. So if it's equal, it's two equal signs. Not equal is an exclamation mark and the equal sign. So this is different basically. So if these two values are different, we append the name to this list. This is one of the useful methods in the list. Remember that the list is also an object. It gives us these methods to manipulate the list. And append is one method that appends at the end of the list one element. So the list starts empty. This is important because even though there is nothing there, I want to tell the interpreter that this is a list object, and the list object has this method here, append. And then I append, and I go appending the names of the residues at the end, those three-letter codes, so that builds a list of residues. And I update the identifier so that any other atom of the same residue will not lead to adding the same residue twice. In the end of this, I return the list. So now I can test this function. I'm going to get a list of strings with all the lines inside the text file by using this function here. If you use open on some file, you get an object that has access to that file, that allows you to read the file in this case. And this object has a readLines function, a readLines method, that for a text file gives you a list with all the lines inside the text file. So it breaks the file into the different lines and gives you a list with all the different lines. Note that I need to put these parentheses here because I'm telling the interpreter to execute that method. If I forget the parentheses, then it will not execute it. It will just point to the method and won't do anything. So now in this PDB source, I will have a list with all the lines in the text file, and this is what I need for my function. So I call my function with this, the source for the PDB file, and store the results in this res list, in this variable. And now I can see what are the first 5 elements here, and the last 5 elements. Note there the -5 to the end. So this is, if I print everything, it's a very large number, but this the first 5 and the last 5 allow me to quickly check by looking at the PDB file if the function is working correctly. So this is another important thing. When you implement something, test it carefully, because once you start fitting everything together, if then an error occurs, it's much harder to figure out where the error happened. If you test each element individually, then you know that when you find an error, it's in the last one that you're working on and not on the previous one. So now we need the masses for the residues. We can go online, Google for amino acid masses. We find a web page with the formula, the mass, and so forth, and we can download this HTML file. So this gets a bit complicated, but this is another common problem. You have something in some strange format that you need to use, and you need to figure out some way of putting it, getting the values that you want. In this case, the HTML file looks like this. You can open the HTML file is a text file with these tags, and you don't really need to know HTML, but you can figure out that these are the rows of the table, TR, table rows, and these are the cells. They have some formatting information there, but then these are the contents of the cells. So you have here ALA, the formula, and the mass, and so forth. So we have all of this here. See, everything, this is one cell, the second cell, third, fourth, fifth, and these are the masses that we want. So what we want here is basically the 3-letter code and the average mass for those amino acids, taking into account all the isotopes and the ratios of the isotopes. So basically we need to extract this and this for the first one, and then this and this for the second one, and so on. So we can do we can look at how the HTML is structured, and we can see that cells start with this TD tag here. The content starts after this font size specifier for the font, and then they end at this less than sign when the other tags begin. And we have all of them in these groups of 5, which have the 1-letter code, 3-letter code, formula, and the math. So we're going to use split to break down each of the line and take out what we need. So we saw an example of split before. In this case, I'm splitting by the comma, but I could be splitting by any of these substrings. So this is how we can implement this function. Note that this function does not receive any argument, because this function can only work with exactly this file we downloaded from the internet. It doesn't work on any other because it's specifically to take data from that file with that format. So this function does not get any arguments, but it still needs the parentheses there because that's part of the syntax. Now we're going to get the source into memory for the HTML file by using the same read line here. This file name, if we give only the file name, it means that we need it in the same folder where we have our code. If it's in some other folder, we can just specify the path where to find it. And now we're going to start with this list with the values that we want, and we're going to append here all these values. So the 3-letter code, the math, the 3-letter code, the math, and so on, and we get all of these. Okay. So we're going to, I'm going to put all these values: 1-letter code, 3-letter code, the formula, and so forth. So we're going to do that by checking if the line starts with this CD, with the cells. So these are the lines with the cells that we want, and we're going to cut the line into this font size. We're going to separate this line where we can find that string. So this is the cutting point. This will be one fragment, and this will be the rest. And we're going to take the second fragment from that. So everything before font size we throw away. We take whatever comes after that. And then we're going to split that on this tag here, the left dash font. So basically we're throwing away that part. Now we're going to throw away this part, and all that's left is the one bit in the middle, and this is what we're going to append here. So this list AA values has all these values here: A, Ella, the formula, the math, and then R, arch, the formula, the math, and everything in order. So all the cells in order from the table are there in that list. Now we want to get the 3-letter code, so we start from the second value, which is this one, and we go 5 by 5 in steps of 5, and we take all of these until the end. And if we want the math, we will start with the 5th value, with the value of index 4, and we do the same thing. So this is what we're doing here. We start with the second one, which is index 1, and we go in steps of 5. And for the math, we start with the 5th one, which is index 4, and we go in steps of 5. So now we take from there the 3-letter codes and the math for all of these. And now we're going to build a dictionary. We start with an empty dictionary. This is the same idea as we did there with the empty string and using append. We can start with an empty dictionary and insert key value pairs into the dictionary. So how we do this? We're going to look through all the indices in the one of these. So these should have the same size. We have for each amino acid type one math. It doesn't matter which one we use, but we're going to use this len function to get the total number that we have here on the list. And then we're going to use this range function, because this range function gives us an iterator that starts from 0 and outputs the same number of values that we have here. So if you use, for example, range 5, you go 0, 1, 2, 3, 4. These are 5 elements starting from 0. This is very useful if you want to look through the indices of an array, because you give range the length of the array, and range outputs all the indices of the array starting from 0 and give exact number of values. And we're going to do that because now this I variable, this index, will be used to point to each of the two lists and bring the two values together. So we're going to create in our dictionary an entry that has as a key the uppercase version of the code that we start there. So the code here you see as A in uppercase, but then L, A in lowercase, and we want everything in uppercase as it's in the PDB file. So we convert this to uppercase, and this is the key for our dictionary. And the corresponding value is the floating point representation, so converting to a number of the string we obtained there with the corresponding math here. So now we are building a dictionary from these two lists, and we do that using this index variable that goes through the indices of the two lists at the same time. And now we return the dictionary. So now we can test this. We run our function. Note that we don't have an argument there because it always uses the same file, but we need the parentheses because we are telling the interpreter to execute the function. And it outputs this dictionary, we store it there, and now we can see what is stored there. And we can check on the table to see if it has the correct values. And the way we can use the dictionary now is by indexing the dictionary with the name with the three-letter code for the residue for the amino acid type that we want. And then it outputs the math. So basically you saw now this second function is also one of those at the edges that we can test as soon as it's done. We can go on to the total mass now, because now we have these two functions, the one that gets the list of residues from the PDB file and the one that can get the dictionary with the masses. So if we bring the two together, we can just add the masses for all the residues and get the total mass of the protein. So this would be the function that returns the molecular weight of the protein by adding all the residue masses here. And it needs to receive as input the source, the text for the PDB file, so the list of strings with all the lines in the PDB file, and the dictionary with the amino acid masses. From this source, it will call the function that lists residues and gets the list of residues from the PDB file. And now it's going to go to look through all the residues. So residue will point to this one, say ser, then ile, ser, asp, and so on, and we'll look through all these lists. And now for each of the lists, it will add to the same variable the mass it's going to get from that residue. Now since this mass is for the residues inside the protein and the peptide bond releases one water molecule, they already have that oxygen and two hydrogens missing. However, at the ends of the protein there is one oxygen and hydrogen on one side and one hydrogen on the other. So we start with this initial mass, which is the mass of those atoms, and then we add everything in between there. So this is also a common operation. You compute something here. In this case, it's the total mass plus the mass of that residue, and you store it back in the same variable. Note that this does not make sense as an equation. As an equation, it will be impossible to find a value that is equal to itself plus something else, but this is an assignment operation. So what you're telling the interpreter is to go get these values, add them together, and put them back in that drawer there, and replace the value that was there. So we are adding things up in the same variable, and we accumulate all the values here. There is a shorter way of writing this, if you want. With Python, you can just put a plus equal sign, so plus before the equal sign here, and then just put whatever you want to add to that variable. But I didn't write it that way because it's a bit more confusing. So if you want, you can write it this way. It works all the same. And then in the end, we have the total mass for the protein. We output it. So now we can test it. We have this dictionary from the previous test. We have the variable with the dictionary. We read the PDB file, so we have all the lines of text from this file, and we send that to our PDB math function and output the result. Now we want to get now we worked on the parts of the math. You see, we have these three functions. They work together to give us the final result. Now we're going to look at the length. It's the same idea. We need to receive the list of lines from the PDB file and extract all the coordinates of the atom. So just going quickly through this, we can have a list of atom coordinates that starts at empty. For each line in the PDB source, if it starts with atom, which is the line that specifies the atom and the position, we extract the text from the x, y, z coordinates. So this is the format here. The line that starts with atom has these coordinates for the position of the atom. So we go to that slice of the string and we extract the x, y, and z coordinates. Just remember that when we are processing a text file, everything there are strings. If you want the actual number, you need to convert this. So we're going to convert this to a floating point number, and we store it there. And then we're going to append to our coordinates a tuple with the x, y, z values. So our list of coordinates will be a list of triplets of values, each triplet corresponding to a position of the atom in 3 dimensions. And now we can test this. We read a PDB file, we send those lines to the function, and we get this list with all the atom coordinates, and we can go check on the PDB file to see if they're correct. So remember that testing is not only seeing if the function runs, but seeing if the result is correct, because if the result is wrong, then you can have a serious headache later on trying to figure out what went wrong, okay? So don't just think about errors in your code as something the interpreter stumbles on and stops working, but the possibility that the code is wrong and is outputting the wrong value. So we check, we compare the values that we get here with the values that we have in the PDB file. Now we need to find the largest distance between any two atoms. We can write this auxiliary function that gives us the distance between two atoms, or between 2 points in general. So each point is a tuple of 3 coordinates. We receive 2 points. We unpack the values on the x, y, z coordinates for the point, and then we compute the Euclidean distance between the two. So this is just an auxiliary function to help us minimize the code. And basically, whenever you have something that you have to do a lot of time, it's useful to write it as a function and then just call the function, because it makes your code easier to read and easier to write and test. And now we can compute the distance between all pairs of atoms. We can make this a bit more efficient, because since distance is symmetrical, if we measure between atom 1 and atom 5, we don't need to measure between atom 5 and atom 1 again. So we can do these 2 loops. We're going to start with the index at the beginning, at 0, and go all the way until the one before the last one. So we're not going to the last point in this first loop. The inner loop inside here will start from the point after the point we're starting to loop here, and will go to the end. So this starts at 0, and this will go from 1 to the end, and this will be 1, and this from 2 to the end, and so forth. So we're only looking at each point and all the points that go after it, and not look the other way around, because that would be repeating the same distance. And the idea of finding the maximum is the same that we did for those capitals. We start with a value that is for sure lower than any of the ones we'll find, for instance -1, because distances cannot be lower than 0. And then whenever we find a distance between 2 atoms that is larger than the maximum so far, we update the maximum here. So whenever we find the largest distance, we update the maximum, and in the end it will have the largest distance of all the pairs of atoms. So now we can test this. We can create a list of coordinates here and just test it to see if it, for example, these ones are at the edges of a cube, so this should be the square root of 3, the distance that it finds, and we can check that by comparing to the square root of 3. So again, this is just one test. You should do several tests in important functions, but the main message here is to check the actual values. Don't just trust that things are working just because it outputs some value. Okay? Now we can put everything together and create our report. So we have our final function that brings them all together. It receives the name of the input file that lists all the PDB files we want to process, and the report file, the output file that where we'll write the report. So now we're going to start by reading the dictionary of the message. We need that one for computing the math. We're going to read all the lines in the input file here. So remember, the input file was this one with all the names of the PDB files we have to process. And we're going to open the output file for writing. By default, when you open a file, you're opening for reading. So if you don't specify anything else, the interpreter assumes you want to read the contents of the file. If you want to write something to a file, you add these arguments to the open function, a W there inside as a string, and this means you're writing to the file. So now this object, out file, gives us access to the report file and allows us to write into that file. If the file does not exist, it will be created. If it exists, it will be wiped, everything, it will be set to 0 length, so all the contents will disappear, and you can start writing into that file. Now we're going to write this first header here. So PDB file math length. And note how you can write tab, this \T indicates that it's a special character, the one you use with the tab key to create tables. And this \N is a line change. So whenever you finish a line in a text file, you need to have that code for the editor to know the line has changed. Because all files in your computer are just sequences of values. They do not have 2 dimensions. They are all in a sequence. What gives you that look of lines changing in a text file are these line change codes that tell the interpreter to represent the rest of the file in a new line. So if you want to write a file that has this aspect with several lines, you need to end each one with this new line character. Okay. So this is the header for our file. We just write this string to our output file. And now for each of the names in our file, we're going to clean the name by stripping away all of these extra characters. This is another thing that you need to take care of. If you want to use the string exactly as it is, as you see it in the text editor, you have to remember that the reason why these are split into different lines in the text file is because they end with this new line character. So this is actually a sequence of characters with the end line character there in the middle. So when you read that from the file, you have these special characters attached to whatever named, in this case the PDB name. But this is a very useful method in strings, strip, which cleans all white space from the edges of the string. This can include tabs, spaces, new line characters, all of those things that are invisible when you're looking in the text editor. So this makes sure that the name does not have all these extra characters, because if it had, then you could get an error not finding the file because the name would not be correct. Now we read all the lines in the PDB source file. We compute the math by calling that other function, PDB math. We compute the length by calling the maximum distance of the coordinates. Note here an example of how you can compose functions easily. The max distance function receives as an argument a list of points, a list of coordinates. The list coordinates function outputs as a result the list of coordinates. So we can say, we can call maxdist by giving it as an argument the output of the list coordinates function when it operates on the PDB source. So this will first call the list coordinates function, compute this list, and then put it in maxdist and compute the maximum distance. You can write things more concisely by combining the functions in this way. And now we need to write the lines for the report. So you don't need to memorize this. This is something I always Google too, because these notations, unless you use it lots of time, it's hard to memorize. But basically you have this format method on a string that allows us to specify a format string that has these curly brackets around the values that you want to place inside the string. And the notation here is that these have the index of the arguments that you're going to provide. So this one is argument index 0, which is the first one, argument index 1, argument index 2. You can specify some formatting options. For example, the the .2f means a floating point number with 2 decimal digits. Then you specify also whatever you want around in the string. For example, here are tabs, and here is the new line. And now you can use format and give it the same number of values that is specified there, and format will compose the string with the right formatting that is specified here. So basically, note that when we compute distances or masses here, we get these numbers with lots of decimal places. But in our report, we want to have things a bit cleaner with only 2 decimal places. So we're going to use this format string in this way. But now you don't need to memorize this, but remember that there is this format, and if you write in Google Python format, you see lots of examples of how to do this. So if you want to write a report or format your results in some specific way, this is a very practical way of composing the string that you want to output. And then at the end, after writing everything, we close the file. This is important. If you just read all the lines in the file and you don't keep the actual object that has access to the file, Python will automatically close the file afterwards. But when you keep the object here and you're writing, eventually you have to tell the interpreter that you finished writing so that everything is written down to the disk and the file is released. Otherwise, you may end up not having anything written in the file because the operating system is keeping it in memory, in cache, before writing. Or you may find you don't have access to the file because the interpreter is still using it, it's still open here. So remember, whenever you finish writing to a file, close it. So this is how we can test everything. We call write report. The input file is those lists to process, and the output file for the masses and the length. So to sum up for this part, especially in this example, I showed you lots of little details, but the idea is not for you to memorize them, is for you to have a notion of what you can do. So basically, you saw lots of different things that you can do, and now you can go back to the notes, to the slides if you need to review this. You can adapt this to whatever problems you need to solve. But this is the important part, is to have this basic idea that you can create functions to separate parts of your code. You can control what is executed, how many times it is executed, and you have these principles of decomposing the problem into small functions. Note that all these functions that we wrote are relatively small. They have about a dozen lines of code or something like that. This maybe is the largest one, but this is basically just using the other ones and chaining everything together. It's not complex. So we broke down a complicated process into small bits, simple parts that we could implement. So this is basically the important part here. Always break down the problem until you know how to solve each sub-problem. It's also important to write clear code and document it. Basically, you can document all your functions with something for the help file. This is useful if you intend to use these functions later or if someone else is going to use them. Sometimes there are auxiliary functions that are not meant to be used outside of that context, so you can ignore those in that case. But the one thing that is very important for the code to be readable for us are the names that you choose. So if you choose names badly, if you say call something X, Y, Z, and so on, then you don't know what is happening there. If you choose your names carefully, you can almost read the code as if it was written in English. So names are very important to make code readable and to help prevent bugs, errors in your code, because if you really understand what is there, then it's much easier to not make mistakes that you could otherwise do. Another important thing is indentation, but Python helps us there because Python forces us to do proper indentation of the code. In other languages, indentation is usually optional, and if you don't do it, it's very hard to understand the code. But Python is very helpful in this. So remember that the idea is that since you're writing the code can be what documents your processing method. and so write it in a way that you can also read it. Not only because it may help someone else use your code, but also because you may have to go back to your code in 6 months, and then you're sure not to remember anything unless it's very easy to read, okay? So one thing that is important also here is to practice. I know that this may not be practical with your schedules, but the credits for this course are about 1/2 of the time here and 1/2 of the work autonomously. So this would be about 60 hours or approximately like that in total. So you should practice about the same time as you have here during the week. That would be in theory what would be ideal. Of course, if you already have some programming experience, probably this is easy. Just figure out how to translate from whatever language you use into Python. If you have no programming experience, then it will be useful to try, for example, to work through these examples in the lectures or other examples in the assignments by yourself. Send me emails if you have questions, or we can see next Saturday what you need. Okay. So you have documentation for Python, or in general, one thing that is useful is Google. If you have internet and you want to do something in Python, just write down what you want, and you'll probably find some examples of how to do it. So as long as you understand the code and can adapt it, you can do lots of things like that. Now, for the tutorial part, you can, depending on whether you want to be graded or not, if you need a grade, you have those mandatory assignments. You can send them all at the end, so you don't need to do them now, but at least you know that you have those for each tutorial part. If you don't need to be graded, just do whatever you want, because it depends on how fast you want to advance, on what exactly interests you most. So if you have your own problems, I can help you with that, and you just see the exercises in the tutorials as suggestions of how you can progress, but you don't need to go at that speed. You can go faster or slower, whatever you want.